Recording. All right. Taking a look at the schedule. We are in week 5. We are pretty much halfway done with this thing.
We're racing to finish.
So now I have to start pouring it on, project-wise, right? Wrong. I don't want to do any more work than you do. Week 5, I'm lecturing on assignment number 6. Assignment number 6 is very short, sweet, and to the point. You get a week to do it. I doubt that you would need a week, but you get a week. So, my gift to you. Looking ahead, I am seriously considering not doing this and substituting something else because, or I may just talk about it and not have you do drawings on it or something. I'm still working that out in my own head. It's just a lot more drafting stuff, and I know that I have sensed and heard some students already stressing out about the amount of stuff you're doing and not having enough time to do it. Yeah. So more information on that later. And then next week, looking ahead just a little bit more, you're gonna create a solid model of a gear, because we're talking about gears for this week and next week. As we progress through our drive chain mechanisms, flat belts and V-belts were first, then we did chains and sprockets, and now we're into gears, which is the most efficient and highest transfer of power from a motor to an object that's being driven. And it would be just more of the same. So, and then what you're going to do is you're actually going to 3D print out your solid model of your gear. Has anyone in here in the classroom scenario, not just folks on the video, lecturing, watching, has not taken either the 199 or the 105 digital design for manufacturing class? Anybody not taken that?
No, I did not have. I took the
Okay.
AutoCAD.
The rest of you have had one or the other, and you've done 3D printing with the MakerBox, correct? Good. Then you can run your own parts. That saves me a lot of work and loading up the models. So we're looking ahead to that. That'll be next week. Those of you that are watching the video lecture portion, you're going to have to try to figure out how to get in here and run your 3D model. That's going to be part of the assignment, I guess. All right. That's the schedule. Looking ahead. So let's look at our mechanisms. There's some definitions in the textbook that I'll get to. Spur gears are toothed wheels fixed to rotating shafts. The teeth of each gear mesh together to transmit rotary motion and torque. So let's see what they have to say about shafts in here. Many parts of mechanisms and machines are connected together using shafts. These are often straight, cylindrical, and made from metal. Several ways of holding pulleys and gear wheels in position on shafts, including grub screws. This particular video likes to call those grub screws. I call them set screws. That's probably the more common term. Maybe this was produced on the East Coast. I don't know. We call things differently out here sometimes than the Eastern folks. Keys and keyways. A more secure fixing involving machining a slot into the shaft and the part to be attached to it. The two slots are then aligned, and a wedge-shaped key, not necessarily just a web-shaped key. It could be a square key, it could be a rectangular key, it could be a woodruff key, which you have done in intermediate drafting when you did the keys, key seats, and keyways assignments, looking at the different ways of attaching, making a mechanical connection. So here's looks like a give head key here. There are also spline shafts. Interlocking splines are machined into the shaft, and the hole in the gear wheel has an even more positive connection to transmit that rotary motion and torque. So let's see what they actually define the little grubs key as. We looked at that before. So again, it's more commonly referred to in my working experience as a set screw. Could be slotted, could be Phillips head, could be hex head. A lot of ways it's just a mechanical connection. A lot of times a little flat spot will be milled out, machined out on the shaft to give that set screw a little more holding force so that it's not trying to put the flat part of the set screw on a rounded cylindrical shaft, and just makes a better connection point. And let's see what they have to say about keys and keyways. Gee, they've got gears, but they still use the V-belt in here. This is a tapered key, or the wedged key, a gib head. This video and also the textbook tends to call the shaft in the slot in the shaft a keyway, whereas I would more refer to that as a key seat, because the key sits in that shaft, and then the keyway is actually the little slot that's machined in a gear, a pulley, a sprocket to hold that mechanically to the shaft. But you'll see it defined either way. Some of the wheels have webs on them, some of them don't. Typically the gears don't really have webs on them, but a lot of them do. Alright, so when you have a shaft that has a spline in it, the interference fit, the hole on the pulley or the shaft is made slightly too small for the shaft. The two parts are pressed together, the friction between them holds them firmly in place. Cotter pins are also used, and rotating shafts have to be supported in some way. Bearings are used to give that support. And bearings are used to support rotating shafts. They may have to deal with one or two types of load. Radial, loads caused by the shaft rotating, and axial, loads acting along a shaft pushing it into the bearing. Bearings are made from materials that slide well against each other so that friction is kept to a minimum. There's plain bearings, also called a bush or bushing, is fixed firmly into a hole in the bearing support. The shaft rotates within the bearing. The bearing in the photo is axial or thrust bearing. Has a little lip on it, which if the loading is along the axis of the shaft, which wants to push that bushing through, then it's resisting that thrust force with the little lip on it. It will allow a shaft to rotate freely while resisting this force along the axis. A lot of these are made out of a sintered bronze material, which is porous, and then it's oil, a lubricating oil of some type is forced into those little cavities. It is a quote-unquote lifetime lubrication, bushing or bearing sometimes, thinking that there's enough lubrication in there that will last forever, which nothing does. But it's turned that. Split bushings or bearings. Bushings can only be used when the part of the shaft that runs through it can be inserted from one end. If the shaft is not straight, such as an engine crankshaft, then split bearings can be used to separate and then be attached together. So this is a split bearing right here, kind of like your piston rings in your pistons and crankshafts in your car. This looks like an oil cup right here that's filled with a lubricating oil that then wicks down into the bearing to keep the lubrication going. Ball bearings get over the problem of having a shaft rubbing against a bearing. A row of hardened steel balls are encased in a cage and roll between an outer and inner race. The outer race is firmly fixed to the component and inner race is firmly fixed to the shaft. Ball bearings are usually lubricated using grease. Friction occurs between shafts and bearings due to them rubbing against each other. Heat is produced and the moving parts can quickly become worn. Aim of lubrication is to separate moving parts, so stopping them from touching each other with a thin film of lubrication. Oil and grease are used as lubricants. Thin oils with a low viscosity, which is a resistance to flow, easily penetrate small spaces and are used on things such as sewing machines. Thicker oils have higher viscosity, less easily squeezed out from between moving parts of machines, suitable for such applications as car gearboxes. And then there's reservoirs and grease cups and all kinds of lubrication aspects out there. This applies to gears, it applies to sprocket, can apply to sprockets, it can apply to V-belts and shafts that are incorporated in all of that design. And then they talk about oil cups, gravity. So if we look at the simple drivetrain here, here's a drivetrain video. So here's our old farm machinery again. 2 gears that mesh together, and they have to have a certain ratio. They have to have a certain degree of pitch on them so that they can mesh. There's formulas involved in figuring what the sizes of gears are in proportion to the design, to torque, and to a lot of things involved there. And now we're back to our common terms that we've been using a little bit of. A simple gear train uses 2 gears which may be of different sizes. If one of these gears is attached to a motor or a crank, then it's called the driver. And the gear that's turned by the driver gear is called the driven. We talked about that with V-belts. I talked about it with chain drives. We just switched them because nothing ever matches that. This is the way it's going to be always and forever, where I had you to have the higher RPM on the fan and the lower RPM was on the motor, and that doesn't happen very often. So they're basically V-belts and pulleys, chains and sprockets, gears. They're used to increase or decrease the speed or power of rotary motion. The measure of how much the speed or power is changed by a gear train is called the gear ratio. Lights are going on. I remember that terminology. The higher RPM is divided by the lower RPM to get your speed ratio. No matter whether it's
Always.
driver-driven application, you want a positive gear ratio on there. In simple gear trains, the driver and the driven gears will rotate in opposite directions. A third gear, called an idler gear, can be inserted between the driver gear and the driven gear to make them rotate in the same direction. These 2 gears here have the same number of teeth, 20 and 20. I'll put a little spin indicator on here, and we'll put this in motion. And because they have the same number of teeth, they should operate at the same RPM. So nothing is being increased or decreased on this at all, and they're spinning in opposite directions. The same as chains and sprockets, the same as V-belts. And if we change this ratio and make this half as much and put it in motion, then the smaller gear is spinning twice as fast as the larger. And there's my speed ratio, 2-to-1. Simple. Not very complex. And if we add our little idler gear in here to this, and we can make different combinations of driven, driver, and idler. We'll just have 20, 20, and 10. Then you can see that the 2 on the outside, the driver and the driven, are then going to spin in the same direction. Maybe that's what is necessary in the design element, and changing those ratios will change the speeds.
Changing the idler won't change the speed.
Right. There's compound gear trains. Compound gear trains involve several pairs of meshing gears used for large speed changes are required or to get different outputs moving at different speeds. Center lathes, like the ones found in school metalwork rooms, have compound gear trains. They transmit rotary motion from an electric motor through to a headstock spindle, and lead gears. Lead screws allow the tool post to move on automatic feed. So here's an old machine with the gear train. It has several sprockets or several gears operating at the same time, spinning in different directions. Compound gear trains often have 2 or more gears mounted on the same shaft. A good example is a car gearbox, which has to fit into a confined space, has to allow the driver to select various gear ratios, and also has to change from forward to reverse. So here is a gearbox, car gearbox that there's a shifter knob in there that can change gears in a confined space. Talked a little bit about gear ratios. Right, bevel gears. There's times when we want to take our motion that's in a perpendicular or horizontal configuration and not have a shaft that's in line with it, but change directions at a 90-degree angle. Bevel gears like worm and worm wheels transmit torque and rotary motion through 90 degrees. Unlike spur gears, bevel gears have teeth cut on a cone instead of a cylinder blank. The rotary velocity of the output gear shaft can be increased or reduced by using different size gears. Hand drills make use of bevel gears to achieve a rotary velocity increase. When the power grid goes out and you've got one of these from your grandfather or your dad like I have, you can still survive because you can hand operate them. They're timeless. I mean, really timeless. Very, very useful pieces of equipment and the theory behind it. So we'll put this one in motion here. And you can see the effect of I can generate a fair amount of torque just by using a hand tool and transmit. So here's our hand drill. Yeah, and here you got these in your garage, you're all set for the apocalypse or the big earthquake. Bevel gears are found in car differential gearboxes. They allow torque and rotary motion to be transmitted through 90 degrees from the propeller shaft through the back axles in order to drive the car forwards. Differential gearboxes are useful because they let the rear wheels rotate at different speeds when cornering. So we've got a little differential gearbox video here. This is actually a scale model of a car, and it goes through several different gear train configurations here. So the drive line goes into the gearbox and transmits the power. Miter gears work in pairs. The bevel gears of equal size with the same number of teeth. Miter gears transmit rotary motion and torque through 90 degrees without producing any change in rotary velocity. So the previous example, one wheel was rotating rather rapidly and the other was a little bit slower. This is going to be, again, if you got one of these in your garage or your grandfather or your dad or something, you're set for the power failure because now you can grind your coffee. You don't have to worry about Starbucks. I'm sure they're out there. It's the same speed, just a little different application. Rack and pinion. Rack and pinion is used to transform rotary motion into linear motion and vice versa. The pinion is a round spur gear fixed to a shaft. The rack is a spur gear with teeth set in a straight line. We have an example right here in the room as I'm using it to mount the video camera. That's a rack and pinion. setup right there, so you can take a closer look at that. Camera tripod. Rack and pinion gears used in drilling machines to allow the user to raise and lower the chuck and the drill with this mechanism right here. Has a rack and pinion internally. To allow rotary motion and linear motion to be produced. Now, when I was a kid, rack and pinion steering was the essence of sports cars and the essence of precise steering rather than other forms. And then this is an example of rack and pinion to open a sluice gate in a dam. So here's our motion here. Rotary motion transmits into linear, depending on what we're trying to accomplish. And then worm gears. Worm gears are used when large speed reductions are required. The worm, which is attached to a driver shaft, has one tooth and takes the form of a screw thread. Like bevel gears, a worm and worm wheel transmit torque and rotary motion through 90 degrees. So we're going to go back to our little model car here and see the rack and pinion, or the worm and the worm wheel, as opposed to rack and pinion, to generate the turning forces in the linkages to turn the wheels. And then looking at this, this is pretty slow motion, but one of my hobbies is model railroading, and the little engines that have power have a motor like this that turns at a rather rapid speed, and to get the scale speed, or so that your little model train isn't running at a scale like 300 miles an hour and always falling off the track, they'll use this drive mechanism internally in there, the worm and tooth, to generate a much slower speed ratio between the motor and the gears of the model that's trying to be driven. And I'm sure there are other model situations as well. And let's stop that guy. And helical gears. Helical gears are quieter and more efficient than normal spur gears. They have their teeth cut at an angle across the gear wheel. Each tooth is slightly curved so that it forms part of a spiral or helix. Helical gears are found in car and motorcycle gearboxes where smooth, quiet, high-speed transfer of power is required. And other situations, I'm sure, that exist out there.
Starter motors.
What?
Starter motors.
Starter motors, yeah. Lots of situations like that. All right. So there are, there's some reading that you should probably do out of the textbook. Oop, that washes it out too much. And that's not enough, but that's what we're doing now. So it talks about gear drives down here at the bottom. Talks about spur gears and pinions versus spur. Pinions gears are usually the little smaller diameter gears that exist, and the spur gears generally are larger than that. It talks about the form as a degree or pressure angle. One part that I'll call your attention to that is on page 23 is this. The 14.5 degree pressure angle has been used for many years. It remains useful for duplication or replacement of gearing. Standard angles of 20 degrees and 25 degrees have become standard for new gearing because of the smoother and quieter running characteristics, greater load carrying ability, and the fewer number of teeth affected by undercutting. Standard spur gears having 14.5 degree pressure angle should have a minimum of 16 teeth with at least 40 teeth in mating pair. Gears with 20 degree pressure angle should have a minimum of 13 teeth with at least 26 teeth in a mating pair. So you have a little more flexibility with that. And that's how they're basically designated with the pressure angle. There is some terminology that you want to acquaint yourself with. There are times when I wish I had a little better document. Let's see if we can get in there. All right. As these mesh together, center line of the gears and a pressure line that exists. These gears do not bottom out totally for the depth of them. So you have a couple of things. You have a chordal addendum, you have a face width, a circular pitch, which is a kind of a theoretical designation on here, a circular thickness, a chordal thickness, a dedendum, an addendum, a hole depth, which is essentially the height or the depth of the tooth, a root diameter, a pitch diameter, and an outside diameter. All of those get put into different formulas to calculate what the gear is going to look like when it's made. As a drafter, you usually don't have to worry too much about all of this terminology. And I think there's even a statement in here in the textbook that drafters generally just go to a catalog and specify a gear, which has probably been calculated out by maybe a mechanical engineer. Although, as you gain experience, you may, and depending on what kind of drafting job you end up with, you may end up getting to do a little bit of this, which brings us to our assignment where you get to do a little bit of this calculation. So there's some things I have to warn you about with the formulas when you get into calculating things. But before we do that, let's talk about drawing gear teeth. The teeth on the gear are not normally shown on the working drawings. Instead, they're represented by solid, broken, and hidden lines, which will be discussed under working drawings. However, presentation of display drawings normally require the teeth to be shown. Since the exact form of an envelope tooth would require too much time to draw, approximate methods are used. The two most common methods are shown in an illustration on page 764. You're going to use a little bit of that when you get into the next week's project of drawing the profile of a gear to create a solid model for it. Do not worry about that because I have put together a sheet of instructions and step-by-step on drawing the approximate shapes of the tooth. It's worked really well as long as you follow the directions step by step. And generally most people have not a lot of problem in drawing that profile and arraying it around in Inventor or SolidWorks and creating a solid model of a gear. It looks a little complicated to start with, but it really ends up being fairly simple. So we're going to start with the simple part, except for the formulas. And a working drawing consists of something that looks like this. This is on page 26. And hold still, book. All right, I may have to do this and use my pointer. So the outside diameter and the pitch diameter and the root diameter are generally shown as hidden or phantom type lines. On your assignment, you are not going to have to draw the face of the gear. All you're going to do is a section view that's over on the side with dimensions that correspond to the assignment itself from the textbook. And then you're going to add in a cutting data chart. This is the information that a machinist would need as basic information to basically go get the specific cutter that's involved with the pressure angle and basically machine out from a gear blank. And that's all we need to worry about from a drafting standpoint. But to be aware of and use the formulas is what you need to get a little experience with. I mean, we do call it design and drafting in our certificate title, so we have to do a little bit of that. All right, any questions so far? I don't know enough to ask a question.
Bingo.
Bingo. All right. I should make a joke like those watching the video lecture, there's a 1-800 number you can call for questions.
Glenn, how do you define the orientation of pressure angle? The line?
Wow, that's a very good question. I don't know if I know the answer to that. Basically, it's worked a lot off of a center line, and it's very symmetrical around the center line. That question may get answered a little better next week when we talk about the profile shape and the instructions for drawing it. Yeah. Okay. The actual assignment is on page 42. I'll slide it up here. Where it talks about assignment for unit 20-3 gear drives. The assignment is also summarized on D2L, and I'll pull that document up in just a minute. The assignment is to make a working drawing for one of the gears. And it's going to be gear number 1, which is down here in the bottom of the chart, which has, as design information, the tooth form is 14.5 degrees. The PD is the pitch diameter, which is 6 inches. The dimetral pitch is 5. And when gears mesh together, for them to mesh properly, you're looking at the dimetral pitch number being the same to allow them to mesh together. The face width is 1. The web width is 0.4. The shaft diameter is 1.10. The hub diameter is 1.9 by 1.5 inches long. LG is long. And the material is MI, which I've tried to find, and I'm not really sure what that is. Could be mild iron. I've looked at a lot of different abbreviations, and I'm not sure where they came up with it. But that's the material designation that we're going to put on the drawing, or you will put on the drawing. All right, you're going to do some calculations to fill in the cutting chart, data chart. The number of teeth can be calculated because we have the pitch diameter and the dimetral pitch. So the pitch diameter is 6 and the dimetral pitch is 5. They just happen to coincide with the cutting chart that's on the example on page 26. Your pressure angle is going to be different, which is going to make some of these numbers a little different in the calculations. For instance, now we go to the actual calculation chart. This one right here. Yay. Let me pull up my drawing real quick. One of the things that you're going to calculate is something called the chordal addendum. Whoop. So the chordal addendum as a calculation. Chordal addendum, also known as corrected addendum, is the perpendicular distance from the chord to the outside circumference of the gear. That's a piece of information that needs to go in the cutting data chart. There's 2 columns for calculating gear cutting data. This column over here to the right is for metric. So you're not going to use that. This one is for English units. The formula is the chordal addendum is equal to the addendum plus t squared. This is hard to see in the formula. This is a t and this is a squared in the formula. Plus 4 times the pitch diameter. So to get this, you have to actually calculate the addendum. And the addendum is a little higher up. So to calculate the addendum, which is the radial distance from the pitch circle to the top of the tooth, over here for inch gears, this is the column you're going to use, and you're going to see that either for a 14.5% or a 14.5 degree or 20 degree, the addendum is equal to 1 divided by the dimetral pitch.
Sure it is.
And if you were to calculate that, or to find that so that you can calculate the chordal addendum, back on page 42 in the information, the dimetral pitch is 5. So you have 1 divided by 5. That gives you the addendum. That then goes down into the chordal. And T out of this, T is the circular thickness. The thickness of a tooth or space measured on the circumference of the pitch diameter. Over here, T is equal to 3.1416, which is pi, times the pitch diameter divided by 2 times n, which is the number of teeth. And you have the number of teeth, which is 30. And you have the, what was it? You have the pitch diameter, which is 6. Or you can use this formula, or you can use 1.5708 divided by the dimetral pitch. If you put the numbers into both of those, you will get the exact same number. So one or the other can be used. Bill.
Where did you get 30 for the number of teeth?
On page 42. Did I make an error?
It says 40, well, no?
I don't see where it
I don't see
says
it
30.
Oh, it's calculated, I'm sorry. So you have your pitch diameter and your dimetral pitch. So the number of teeth, number of teeth is equal to the pitch diameter times the dimetral pitch.
Okay.
Pitch diameter is 6, dimetral pitch is 5, 6 times 5 equals 30.
29 plus 40.
That's where you get your number of teeth.
Got it.
All you have to do is read the formula and follow the yellow brick road to get to the end. Okay, the drawing itself. In past classes and past years, I have suggested using a table to create this, just for the experience of creating a table. They're a little harder to manage sometimes than just plain using geometry. And I decided to give you an option. And to give you the option, or to give you a little guidance in how to create the table and the measurements that we're looking for, I put dimensions on here. Which means that you could use geometry, you could use lines to create the table with these dimensions or measurements on it. It's 1-to-1 ratio, it's a full size, and then gave you the size of the text. This is 0.12. And all of the rest of the cutting data chart is 0.10 in height. This is 3.95 inches, this is 0.45, this is 0.35. TYP means typical, which means that
From that point
it's
down.
0.35 height of all of those horizontal lines in a table, a chart that you could create. 2.75, and this is 1.98 distance here, roughly. I mean, it doesn't have to be exact. It just gives you something to go on. This would be centered. This would be sort of middle left justification over here. This would be middle center. The thing about tables is getting the right numbers and making sure that you're suppressing the 0 and that you're getting 3 decimal places in there so that the rounding comes out to what the answers are. Yes, the answers are on the drawing. You now need to do the calculations based on the formula and attach your calculations, or at least hand them in, because I'm asking for an electronic copy at this point rather than a hard copy of the drawing. You need to hand in your calculations to prove that you get these numbers in here.
And that's all written out in the assignment.
Pretty much, yes. Yes.
So we're submitting a drawing and a file showing our calculation.
Yes.
Okay.
Or doing it as a Word document, or hand lettering in your nice drafting fundamental hand lettering styling, showing me that your calculation, what your
Calligraphy is
calculations
not
are.
accepted.
Hmm?
Calligraphy?
No.
So you,
This is block lettering.
so you say you want the electronic on this, on the
Yes,
calculations?
I'm saying that I will accept an electronic file of this rather than
A paper one?
42 copies on paper. I am hopeful that with all of this information in front of you, as an example, I don't think I should be correcting bad data.
So you saying you want the calculations electronically and the.
I will take the well, it's gonna probably be easier if you just hand the calculations into me,
Okay,
and then I can equate that with your electronic file.
okay, and then the electronic one, you want
That drawing.
electronically.
Correct. I want the drawing electronically. Because I have not created an assignment folder for the calculations, which I can do. I can go in so that you could, if you wanted to make a Word document out of it, or even a PDF, I've had some PDFs submitted. You would have a folder for the drawing and for the calculations, so I can go in and do that. I can create that pretty quickly this afternoon. Okay. In D2L, you have in the content tab, you have a module called assignment number 6, working drawing gear number 1. You have the assignment. Which basically replicates the instructions from the textbook here, except that it's going to be a working drawing for Gear 1 based on the information in the chart shown on page 42. Single spur gears. Include in your drawing the cutting data chart per the example on page 26, as well as the example drawing, which is up on the board, which is also an example drawing included in D2L, KIN 255-6. Included on D2L. Assignment number 6, content module. The title is working drawing gear number 1. That text type is 530 seconds. The drawing number is KIN 255-6. Text type 1/8 of an inch. Material is MI. Text type 1/8 of an inch. Drawing scale will be full. The text types for the drawing scale can either be 1/8 of an inch or 3/32 of an inch. And then your name and your date, which is 3/64. The working drawing of gear number 1 is to be completed by 5 p.m. Wednesday, May the 3rd. You can submit an electronic copy of the assignment to the assignments folder in D2L, or if you're on campus, in this room, or even in, it should work in Tabor 117, or you can drop the electronic file on campus in the classroom file folder on the desktop, which I'll show you. Then there's a CAD folder that comes up with that. Then there is CAD 255 kinematics drafting folder, project files folder, Monday, Wednesday folder, and your name folder that you could drop it into there on campus. Or you can use D2L. D2L is probably a little easier, but I'm making provisions for both of those.
So is this a B size or an A size drawing?
It is a B-size drawing,
Okay.
11 by 17. Okay, so there's your assignment in writing. And back on that same tab, there is a PDF of what the drawing is supposed to look like, as well as the one that's up here on the whiteboard that you can take your smartphones out and take a picture of.
So you want us to draw that
I want
Make
you
the
to
table.
draw that and put all of that information on there.
and make the little table
And make a little table and put the cutting data.
and call it
information
drawing
on it.
Kim 255.
You can either make geometry for the table chart, or you can use a table command.
Okay,
Alright, so it's there,
I got it.
and you are going to prove that these numbers are correct, that Mr. Truman has not given you false data here. Because you never know, it just might be bad numbers. You wanna check it. And also, there is a B-size title block
What? You're being nice again?
available. How much more do I need to do than that?
Can you make my dinner?
Not much. I am not gonna draw it for you. So there's written instructions, there's verbal instructions, it's an easy drawing, it's middle of the term.
Any questions from home?
Yeah, any questions from home? Dial 1-800,
I don't care.
no joke.
So, title block, do it has to be scaled, or it's gonna come in the right size?
The title block does not have to be scaled, it is a 1-to-1 ratio.
Everything's one.
It is a full scale drawing, 1-to-1.
Yeah, no 4s, no 12s?
Are we done yet?
No stress, no mess, easy peasy lemon squeezy as they say nowadays, right?
No.
No.
Okay, see, I'm being really easy this one, then I can just really pile it on you.
On the
Last
next
couple
one,
weeks.
you retiring?
I don't think I'm going to.
Yeah, no problem on you retiring.
Are we done yet?
Alright, I think we're done. Have fun.